for coming to my talk. So I'm dealing here with the fracture behavior of pure tungsten, which has been a topic we're dealing at the Schmidt Institute for many years in the framework of our activities in the neurofusion program. And today I will present work that has been performed by Pillmeier and Daniel Firneis, and in the end I will also give a little outlook on the current PhD work of Michael Pegritz. Yeah? So the motivation to deal with the fracture behavior and also with the fatigue behavior of pure tungsten is that many parts in future fusion reactors will be made from tungsten. Tungsten alloys due to the exceptional properties of tungsten as it can withstand this harsh environment within the plasma vessel. And one drawback that tungsten has is the inherent brittleness and the very high ductile to brittle transition. And to mitigate this problem, different toughening strategies have been developed over the last years, or actually decades, for instance, by alloying, what we all know from university for sure. Then other groups have worked on synthesizing composites, as you see here, such tungsten laminates or tungsten fiber reinforced tungsten composites. And the third strategy is by microstructural design, which can be done by, for instance, by thermomechanical processing or by methods of severe plastic deformation.
Could you please speak a bit louder?
Oh, sorry, I thought it was loud enough, sorry. So, so the third strategy would be by microstructural design, which can be realized, for instance, by thermomechanical processing or by methods of severe plastic deformation. And with such approaches, you can get such ultra-fine-grained microstructures in the form of foils or wires. And we were now in this present study interested in the fracture properties in terms of the quasi-static R-curve behavior, and we also looked into the cyclic behavior, so to say, into the fatigue work behavior, into the SG behavior, which could also be important when you think of a pulsed operation mode of such fusion reactors. Okay, let me start with the material that we have been looking at. I have to say the resolution here is unfortunately really bad. What you see here is our testing material where we made our experiments with. It was tungsten, a tungsten plate, which was cold rolled to certain sheet thicknesses, which is equivalent to certain degrees of deformation. And what you should see here is that the grains, they become through this cold rolling continuously elongated and also thinner. And these are results you see here for this RD and D plane. And when you look at the other plane, at the TD and D plane, you would also have more or less the same structure, only that the grains, the grain length would be shorter. Yeah? So all in all, in the three-dimensional representation, you would have a pancake-like grain shape. Yeah? In addition to this continuous elongation process that we see here, we have also a strong increase of the high angle grain boundary fraction and the formation and the strengthening of a pronounced rotated cube texture, as you see here in this example, where we have the 1-1-0 planes with a high fraction of 1-1-0 planes on this basis here. Yeah. So this was the testing material, and we made then R-curve experiments. The other experiments were a little bit difficult. We had here samples where the notch was introduced perpendicular to the rolling direction, and we were working with two different specimen dimensions. That's the unfortunate thing for reasons of comparability. We had to do this due to buckling issues we had here. Yeah? For different sheet thicknesses we have been looking at, so from 2 mm down to 0.1 mm we made the experiments, and for the thicker sheets, the fatigue pre-crack was introduced by compression loading, and for the very thin sheets, we had to make only a fine notch, but it was only possible to make a fine notch with a focused ion beam station. So the experiments were performed at room temperature and at some elevated temperatures, and the crack growth length, or the crack length, was measured with the direct current potential drop method. And the results in a nutshell are shown here. So we get an improvement of the fracture resistance on the one hand side by deformation. As you can see here with the examples for the 2 mm, 0.5 mm, and 0.1 mm sheet thickness. And also by a little increase of temperature, we have a pronounced R-curve behavior in this material. And the reason for this you can find on the fracture surface. You get here such eliminations which will change the stress state at the crack formed from plane strain to plane stress. And in addition, we also have here strong necking of the remaining ligaments. And in competition to this delamination formation, we also get transcrystalline fracture in the samples, which propagates approximately under 45 degrees with respect to the pre-crack. Yeah? And with increasing deformation, the area of these delaminations becomes larger and the R-curve behavior becomes more pronounced. We were also interested now to measure the fracture toughness in another direction. You see here, we wanted to measure the fracture toughness in this splitting direction. Where we also see here grain boundary fracture occurring, and this we did with micromechanical experiments, and we found that the initiation toughness is only about 2.5 megapascal square root meter, and again we also had a pronounced R-curve behavior which can be explained by the formation of shear ligaments, as you can see here probably. Yeah? Okay, now I come to the FCG behavior. Here we investigated only 3 different thicknesses, so the thicker ones and the very thin one, because the very thin one was the most interesting. We worked with CT specimens and with SEN specimens. We had different crack orientations, so the crack was running perpendicular and parallel to the rolling direction, but also under 45 degrees. The crack length was again measured with the direct current potential drop method. We used 2 different load ratios to account for mean stress effects, and the crack length was again measured with the direct current potential drop method. The loading scheme we used was the load rising method, so we measured the fatigue crack growth curve from the bottom going up with constant load steps, as it's shown here a little bit, so where the load is incrementally increased, and then we have here some crack growth. We get points for the cyclic R-curve, and starting from the point where the crack doesn't stop anymore, so above the threshold value, you can generate the FCG curve from this data. Yeah. Here are now the results summarized for the thicker sheets. Yeah. You see here the fatigue crack growth curves. They are only very short. Interesting to mention is here that we get very high threshold values, values of about 20 megapascal square root meter. And as I already said, we only have a very short regime of stable crack growth before the specimens break. What we also see here, that we have here in these threshold values also a distinctive organization tendency. And when we look at these R-curves here, so you see here the R-curves for the 2 mm material and for the 1 mm material, we see here that even for the high stress ratio that was applied, we still have an R-curve behavior, which is most of the times not the case when you think of the closure mechanisms, or closure mechanisms will be less prominent at these high stress ratios. So what is now the reason for the occurrence of this R-curve. This I will show you on the next slide. I show you here an example of the fracture surface of such a sample with a 1 millimeter thickness material. And in the overload area, you would have transcrystalline fracture. In the area of stable crack growth, we see these elongated grains which fail in an intercrystalline and transcrystalline manner. So there's a mixture of both types. And in the R-curve region, which is here, we see oxides and debris. So the main reason for the R-curve here is the occurrence of oxide-induced crack closure. Yeah? But I said we also have R-curve behavior for the high R or stress ratio, and this we can explain when we look here at the fracture surfaces for the low and for the high R ratio. You see for the high R ratio we have the formation of these deliminations already in the area where the R curve occurs or builds up, and that means we have again very thin ligaments which stay under plane stress, or in other words, we have here plasticity, reduced crack closure under plane stress, which contributes to this R curve. Yeah? Okay, then I come already to the results of the thinnest materials, so the most severely deformed materials, the 100 micrometer foil. We have here again this behavior of a cyclic R curve. This has more or less the same reasons. So for the low R ratio, it's based on oxide-induced crack closure, and for the large R ratio, it's based on the occurrence of plasticity used in crack closure. More interesting is now the fatigue crack growth curve. You see here the results for the LT and for the TL orientation, and we see here now a pronounced Paris regime with Paris exponents, depending a little bit where you measure them exactly, but they are always somewhere around 2 to 3. Yeah? And these are exponents which you actually also would find in comparatively seen very ductile materials like steels. Yeah? So it seems that also in such a material the crack growth can be described by a crack tip planting and resharpening process. Yeah? Again, as you can also see from these curves, we have this pronounced anisotropy. Again, we have orientation-dependent thresholds, but we have here now also orientation-dependent crack growth rates, where for the TL orientation we have the highest crack growth rates, so the lowest crack growth resistance, and the lowest crack growth rates for the LT orientation. And we made also experiments for this 45-degree orientation. There you see the values are somewhere between. So the behavior of the 45-degree sample is somewhere between the TL and LT. And that's actually an interesting thing to say, because when we think of this rotated cube texture, we see that cracks running in a transverse direction or in a rolling direction, they experience more or less the same crystallography. So they're always a very high fraction of one O planes, and you would actually not expect such a orientation dependency in the DN grains. Yeah? The reason for this you can find maybe a bit better on the fracture surface. So on the macroscopic view, you see again we have this formation of delaminations. They are needed to stabilize the fatigue crack growth, so the fatigue crack growth and this pronounced Paris regime is possible. And on the fracture surfaces, you see here again very elongated grain structures. In the TL orientation, it's a mixture of intercrystalline and transcrystalline fracture. For the LT orientation, it's mainly transcrystalline fracture, I would say. I'm sorry, the picture's a little bit too small. And the reason, what we think, why we have now this anisotropy, is that when the crack propagates here perpendicular to the rolling direction, the crack will see a higher fraction of grain boundaries due to this pancake shape. The crack has to deviate from his directions when he goes into the next grain, and this would be then a geometrical shielding effect to explain this difference in the crack growth rates. Okay, and we also have anisotropy in the thresholds, and this anisotropy changes. So for the 2 and 1 millimeter material, the LT orientation has the highest thresholds. This changes to the TL orientation for the 0.1 millimeter material. And this is a little bit difficult to explain, and we have no clear solution to this, but it may be connected with a change in the contributions to crack closure, also changing of the contributions of plasticity-induced crack closure and oxide-induced crack closure. And what we also see is we have strong influence of the test frequency. We made here an experiment where we changed the frequency from 20 Hertz to 1 Hertz down to 0.1 Hertz. And 0.1 Hertz are these points up here. And we have here a triplication of the crack growth rate. Yeah? How can this be possibly explained? It could be possibly explained by a strain rate sensitivity effect, meaning when the deformation speed is lower, also the yield stress will drop, and this would result in an increase of the cyclic crack tip opening displacement, and lastly, in a change also of the crack growth rate. So with this, I'm already at the end because you were standing already for a long time. What I wanted to show you is for monotonic loading, the RT flexion behavior changes from a brittle to a fully ductile behavior with increasing pre-deformation. This is equivalent to a shift of the ductile to brittle transition to room temperature and below. In the case of cyclic loading, we have pronounced R-curve behavior. After severe cold rolling, we can obtain stable fatigue crack growth. Even at room temperature, we have Paris exponents in the range of 2 to 3, which are typical of ductile materials, and we have orientation-dependent crack growth rates and long crack thresholds. And in future, we will expand these investigations then also to more fusion-relevant temperatures. And there is a project recently started where we test now the tungsten quality and make these experiments at somewhat higher temperatures where the material is already on the ductile, also on the upper shelf. And this is an example of the material which will be then really put into the fusion reactor. Yeah, and with this, thank you.
Thank you for this very interesting presentation. We have time for one question. Who was first? Go ahead.
So, have you guys stressed strain curves for this material in this condition?
This is another group, so it has a ductility. So another group of has also worked on this topic, and they made tensile tests, and it also has tensile ductility of about 1% in this 100 micrometer foil.
So dependent on orientation, it varies probably a lot.
Yeah.
You want to ask quickly, Johan?
Well, yeah, on slide 9 actually, where you said you had oxygen-induced crack closure.
Yeah.
I tried to look at the SEM and I didn't see it, so can you do a positive identification of that?
Sorry?
It's like from this SEM imagery. Yeah, okay, maybe you can just explain it.
You would see many little spots, yeah? So really small spheres, I would say.
And yeah, but did you also do EDX analysis to be sure that the oxides are there, or?
This is a difficult thing because the oxides are not very large, and I'm not sure if with the interaction volume you would really measure the oxide really stemming from the particles or from the surrounding.
Oh, okay. Yeah. Okay. Yeah. Thanks. Thank you.
Thank you.